Welcome to this upper sixth core pure video on complex numbers. This is on the exponential form of a complex number and what we can use it for. So I'm going to start by sharing the visualizer. And what I've done is I've written a complex number in its modulus argument form. So just a reminder that if we've got a complex number z, its modulus argument form is r times cos theta plus I sine theta, where r is the modulus and theta is the argument. And what we're going to see is that we can also write z in exponential form. So its exponential form is z is equal to r e to the I theta. So r is still the modulus, theta is still the argument, and I is the imaginary number. So I squared is -1. So let's just see quickly where this comes from. We're going to have a look at, and then we'll see what use it is. So we'll have a look at the formula book now. So let me just share with you. This is the PDF form version here. This is page 18 of the formula book, and we've got up here Maclaurin's and Taylor's series. Now, you will cover Maclaurin's series separately, but I just want to show you them for now. So we've got e to the x is equal to, it's an infinite series, 1 plus x squared over 2 factorial plus, and then there's the general term x to the power of r over r factorial. So this would be x cubed over 3 factorial, x to the power of 4 over 4 factorial, and so on. We've also got infinite series for sine of x and for cos of x. So let's just look at cos of x first of all. It's 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial, and so on. So you can see that it's got even powers. Sine x, very similar, starts with x, alternates positive and negative, and it's got odd powers. What we're going to do is we're going to use that to show where this exponential form of a complex number comes from. So let's go back to the visualizer now. Let me just share that properly with you. So we're going to write out e to the x. So e to the x, this is the Maclaurin series for it, is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the power of 4 over 4 factorial plus x to the power of 5 over 5 factorial, and so on. Okay. What we're going to do is we're going to say let x equal I times theta. So I times the argument of our complex number. We're going to substitute in, we're going to say e to the I theta then is equal to 1 plus I theta plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the power of 4 over 4 factorial plus I theta to the power of 5 over 5 factorial, and so on. Now, we can simplify this, and we can say this is 1 plus I theta. I squared is minus 1, so this is minus theta squared over 2 factorial. I cubed is minus I, so this is minus I theta cubed over 3 factorial. I to the power of 4 is just 1, so this is plus theta to the power of 4 over 4 factorial. I to the power of 5 is again minus I, positive I, so plus I theta to the power of 5 over 5 factorial, and so on. And then what we're going to do is we're going to split this out into real and imaginary parts. So this is 1 minus theta squared over 2 factorial plus theta to the power of 4 over 4 factorial, and so on. We've got even powers, and they're alternating positive and negative. Plus I times, this is theta minus theta cubed over 3 factorial plus theta to the power of 5 over 5 factorial, and so on. And these are the two series that I drew your attention to in the formula book. So this is now, this is cos theta plus I sine theta. And if you want to check that, go back and have another look at page 18 of the formula book. So this was e to the I theta. We really want our z to be r equal to the r e to the I theta. So we just say that z is equal to r e to the I theta is equal to r cos theta plus I sine theta. So we've now got exponential form of a complex number. So that's where it comes from. What we're going to look at now is what use this is to us, or first of all, some examples of writing complex numbers in exponential form, and then we'll see why we are interested in that and what use it is to us. So if we look at the examples in the course workbook, question 1 asks us to write these complex numbers, which are in the first two cases in modulus and argument form, in exponential form. So for A, we're going to say, well, the modulus is 2, the argument is pi over 12, so z is equal to 2 e to the pi over 12i. For B, we've got to be careful because we've got a minus sign here. So we're going to say z is equal to, now we can change this from root 3 cos of pi over 6 minus I sine pi over 6 to root 3 cos of minus pi over 6 plus I sine minus pi over 6. So root 3 cos of minus pi by 6 plus I sine minus pi over 6. So what we've done by changing that to a plus there is we've got it correctly in modulus argument form. The argument of this of z here is not pi over 6, it's minus pi over 6. So z is equal to root 3 e to the minus pi over 6I. And then for C, what we want to do is we want to work out the modulus and argument of minus 1 plus 3I. And what we're going to do is we're going to do a quick little sketch for C. So I'm going to draw that like this. So this is our real axis, RE. We've got minus 1 plus 3I, so we're going to put our complex number there. That's Z. This is 3I. This is minus 1. And if we draw this in here, this is the argument. So the radius is going to be the square root of 3 squared plus 1 squared. So R is equal to root 10. And the argument theta is going to be equal to, well, I like to work out this angle, and then we're going to say it's pi minus that angle. So it's pi minus, here we've got opposite and adjacent, so it's tan to the minus 1 of 3 over 1, so tan the minus 1 of 3. That comes out to 1.8925. It's not an exact fraction of pi. So we can write Z is equal to root 10 e to the 1.8925 I. Question number 2, express Z is equal to 3 e to the 17 over 4 pi I in the form r cos theta plus I sine theta. Well, what we're going to do here is we're going to say 17 over 4 pi is equal to 4 pi plus pi over 4. So the argument of this complex number is pi over 4, because that 4 pi means we're going round 2 pi again, and then another pi over 4. So we can say, so Z is equal to 3 e to the pi over 4 I. This is still in exponential form, and then we can say, so Z is equal to 3 is its argument, is its modulus, sorry, cos of pi over 4 plus I sine pi over 4. So we've converted a complex number from exponential form back into modulus and argument form. Okay, so let's go on to see why this modulus argument form is useful to us. So it really just follows on from what we found out in year 1 about the rules for multiplying and dividing complex numbers when we have them in modulus and argument form. So if we're multiplying complex numbers, we multiply their moduluses, and we add their arguments. If we're dividing Z1 by Z2, we divide their moduli, So Z1 divided by Z, modulus of Z1 divided by modulus of Z2. And we subtract their argument. So argument of Z1 minus the argument of Z2. And we can do exactly the same thing in exponential form. So if we're multiplying, we just get R1, R2, and we get the sum of the arguments, dividing R1 divided by R2, and the difference of the arguments there. So we want to express this calculation, or the result of this calculation, in the form x plus iy. So what we are going to do is we're going to work out the product of the arguments. So that's pi over 6 plus pi over 3, which is pi over 2. So we can say the result of that calculation is equal to 2 root 3 cos pi over 2 plus I sine pi over 2. And we know that cos of pi over 2 is 0 and sine of pi over 2 is 1. So this is just equal to 2 root 3 I. In other words, our x is 0 and our y is 2 root 3. Let's write that down. X equals 0, y equals 2 root 3. Okay, let's look at question 2. Given that z is 2 plus 2i, the imaginary part of zw is 0, and the modulus of z times w is 3 times the modulus of z. We want to find two possibilities for w. So the first thing to look at here is the imaginary part of zw equals 0. Well, that means that zw is a real number. So we can say Im of zw equals 0. So zw, the number zw, is a real number. And it can be positive or negative. Or negative. Now, we know that the modulus of zw is the modulus of z times the modulus of w, and we can find the modulus of z. So modulus of where are we? Z is equal to the square root of 2 squared plus 2 squared. So that's root 8. Actually, we don't need that, do we? We can say that the modulus of zw is equal to 3 times the modulus of z. So modulus of w must be 3. We know that it's a real number, positive or negative, so W is equal to, no, we don't know that. Modulus of W is 3. Let's find the argument of Z. That's what I meant to do. So arg of Z is equal to pi over 4. This is because it's got the same real and imaginary components. So is equal to pi over 4. And then we can say let's get rid of that. So the argument of W, well, we need to add something to this to make ZW a real number. That means that we want the argument of ZW to be either 0 or we want it to be pi. Let's write that down. Arg ZW is equal to 0 or pi radians. So we want arg of W to be equal to minus pi over 4 or 3 pi over 4. So W is equal to 3e to the minus pi over 4i, or 3e to the 3 pi over 4i. Right, I'm going to end that video now. We'll go on to the next video is on de Moivre's theorem, which uses the exponential form of complex numbers.